Hey, what's up YouTube? In today's video, I'm going to show you a recent experiment I did to create interactive tall grass. What you're looking at is a custom capsule-to-capsule physics system. Nearby grass instances are quote-unquote injected into a simulation in the form of capsules that can be pushed around by your own character's capsule. And those capsules' up vectors are sent to those grass instances via per-instance custom data to bend the geometry. That means there's no expensive swap with a physically simulated skeletal mesh, right? What you're looking at are plain simple mesh instances, period, and this is quite an efficient way of doing things in principle. I've seen quite a few systems where nearby instances are swapped with physically simulated skeletal meshes, and that can work. I've done similar things way back, but swapping has a non-negligible cost, not to mention the cost of rendering many skeletal meshes. Plus, I like to experiment with all kinds of techniques. Now, I said this particular technique is quite efficient in principle. Why in principle? Well, because I've built this custom physics simulation using nothing but blueprints, and for that sole reason, it's really not that great performance-wise. It's not like there are a lot of complex math to compute or anything, just that the blueprint virtual machine has quite a lot of nodes to evaluate, and that for as many instances there are to simulate, for as many interactive actors, your character, nearby enemies, and so on. That's a nested for loop essentially, and so you can end up with thousands of nodes the virtual machine has to evaluate, and performance can tank quite fast. There's not much you can do about it, sadly. That being said, I ported a similar system to C++ a while ago just to see how it would perform, and yeah, it becomes a viable option and you can go nuts. However, a simple C++ implementation of this technique is still not ideal because it's entirely CPU driven, and ideally you'd create a GPU driven system so you can go bananas with the simulation, but I'm not there yet. I still have quite a bit to learn, so for now, simpler things it is. Now, that's assuming you want a per-instance simulation, else I've built systems relying on render targets and using other methods as well. I'm really not pretending this is a great solution, and to be honest, I don't consider this technique particularly good, it's just one worth sharing, I suppose. Also, because this is entirely CPU driven, it's quite hard to tie this system with whatever win system you might have built, right? Likely some kind of scrolling texture or something alike that lives entirely on the GPU in shaders, thus not easily accessible to the CPU. Finally, because the simulation is computed per instance, each instance is in some kind of bubble on its own, right? So an instance can't affect nearby instances, nor can it be affected by them. It would be cool to have that, but yeah, that's just not doable with this system, at least in blueprints. Way too taxing. So yeah, this system is quite limited in its current form, but again I thought it was interesting enough to make a video about it. And as always, keep in mind the scope of your project. This system may be limited and not perform too great in the grand scheme of things, but it may very well be enough for some kind of minimalist game or small scale application. Always keep that in mind. Anyway, enough rambling, let's dive into it, shall we? Alright, this system is made of two blueprints. First, there's an actor component. It doesn't do much. On begin play, I first gather all Foliage actors and loop through their Foliage instance static mesh components. I do that to only gather the list of components that make use of the Foliage types I want actors to interact with, say that one. Next, this actor component is meant to be added to a player controller, so gets its owner and cast to a player controller to get its controlled pawn. If any, see fits a character to get that character's reference, but also its capsule's half height and radius. That information is sent to this addParticipant function to build a list of all actors that can interact with Foliage instances. So obviously your own character, but it could be nearby enemies, pawns, or any other actor really, as long as you provide a made-up capsule half height and radius for it, right? Next I start the system, meaning I merely enable tick on that component because it doesn't tick at first. On tick then, make sure there's anything worth ticking. Here I loop through all participants, so again your character, nearby enemies you'd add to this list, and so on. Next I loop through all Foliage instance static mesh components I gathered on begin play and check if there are instances around this one participant. By the way, that radius shouldn't be too large, else it would gather too many instances and that could tank performance. But it shouldn't be too small either, just large enough to detect instances around participants in time for the proper capsule collision check. Anyway, if there are instances nearby, I need to quote-unquote simulate them, meaning handle some kind of collision and physics algorithm, right? The issue is that I may have multiple foliage components, and so I may need to simulate instances that share the same instance index. Say 2 instances, both at index 0 in their respective instance component, right? So to make my life easier, for each instance component, I spawn a manager. That ensures each manager manages a single foliage component at a time, and thus deals with unique instance indexes, if that makes sense. And a manager is a simple, lightweight UObject. It has a few variables exposed on spawn, namely this foliage instance component. That way, this manager, this UObject, can keep track of the instance component it's managing. And I also used a map to know what's the manager associated with a given instance component, right? Next, I simply tell that manager, hey, those instances are around a participant, they may need to be simulated. And that's actually pretty much all there is to this actor component. So all it does in a nutshell is 1. Gather foliage instance static mesh components that make use of a certain static mesh or meshes. 2. Gather a list of actors that may interact with that foliage, what I called participants. 3. For each participant, for each instance component, see if there are instances nearby. If so, forward those instance indexes to a manager associated with that particular instance component. And that happens on tick. Now, I would limit the tick rate of this function because this really don't need to tick at a high frame rate. But I ended up using this actors component tick for something else, more on that in a second. Still, this system isn't as optimized as it could be. Speaking of performance, there's one unknown, I might say. This node. How fast or slow is this? I have no idea. Well, I do, but let's assume I don't. So let's go to GitHub and search for this node's name. Let's try instances overlapping sphere. Instance placement hash, nope. Landscape proxy, nope. Instance foliage actor.h, could be it. Let's search for sphere. Get overlapping sphere count isn't the function I'm looking for, nor is that one. Let's keep looking. Now, it's highly likely the function I'm looking for isn't part of a foliage class of some kind, because that class likely inherits from the instance static mesh component class, and that's where I think I'll find that function. Speaking of which, here it is. It's the header file, but still, let's have a look. Search for sphere. Yep, there it is. Get instances overlapping sphere. It outputs an array of integers, has a vector center, a float radius, and a boolean world space, so that's indeed the function I'm looking for. However, that's the declaration and I'm looking for the implementation. So let's find the instance static mesh component.cpp. Maybe that one, let's see. Yep, there's the implementation. So it looks like it just naively loops through all instances to perform an intersection test between that instance spherical bounds and a sphere of a given radius. And that intersection test is a squared distance check, so there's no square root. Great, that's fast. So yeah, looks good to me. Now I'm not sure how well this function scales with millions of instances, but that's unlikely to be our case, I suppose. Obviously, I wasn't actually hoping to find an issue. This was just to show you that it's most often quite easy to know what a node does under the hood. And it's always best practice to know what you're working with and to have a good understanding of what's costly and what's not. Feel free to dig in a little bit, you really don't need to be well versed in C++ to understand what this function does and to have a grasp on its cost, in my opinion. Anyway, that's the actor component. The heavy lifting happens in the manager blueprint. So let's check its activate instance function. First, here are a couple of safety checks, then I loop through all nearby instances that were sent. Now that manager keeps track of all instances currently simulated with a simple integer array, which means if that instance index isn't contained in that array, that instance isn't yet simulated. And obviously it may need to be, but only if its capsule is actually in contact with this participant's capsule, let's say your character. And to know that, I first get that instance transform in world space, construct that instance capsule segment from root to tip, get the participant's location, and construct its capsule segment as well, so from feet to head for our character. Now you may notice I don't really build two capsules, just two segments. Well, that's because a capsule-to-capsule intersection test is just a matter of finding the two closest points between these two segments. And if the distance between these 2 points is smaller than both capsule radius combined, then those two capsules intersect each other. Now that sounds easy on paper, but that actually requires quite a bit of math. Side note, you could build a much simplified version of this and assume a participant is no longer a capsule, but a sphere. With such setup, you just need to get the closest point on this segment to that participant's position, it's very little math, and do a distance check. But with 2 capsules, thus 2 segments, well, it looks like it's not that easy. Now that's well beyond my own skills, so I looked around and found some complicated code and some less complicated code. I was a bit surprised, to be honest with you. Capsules are quite popular because it's quite a useful shape to work with, and capsule collisions are supposedly notoriously easy and fast to perform. Apparently not so much, I don't know, I could be missing something here, but that doesn't look that simple to me, and it's definitely too much to be ported to blueprints somewhat efficiently. That being said, I eventually found that piece of code, it didn't look that bad, so I ported it to Blueprint, and it was working great, but was still performing quite terribly. Now this is nothing expensive, but do that say 100 times on tick and the cost kinda skyrockets. Again, you can only do so much to file the Blueprint virtual machine overhead, that's just too many nodes to evaluate and it has a cost. Eventually I found out that there's a built-in node that does just that. I initially searched for it, but I suppose I did that with the wrong keywords or something. Anyway, cool, I could get rid of that blueprint stuff, use that node instead, to figure out the distance between these 2 capsule segments and get a very nice performance boost. And again, if that distance is smaller than the 2 capsules radius combined, there's a collision. Which means that instance that wasn't yet part of the simulation really needs to be simulated to physically react to that collision in some ways, right? So that instance index is added to this array, it's now simulated, so that will be false next time this instance is sent to this manager via this activate function, at least as long as it's simulated. I also add an entry to that simulation stack. That struct contains the instance index it's linked to, and at first its capsule's endpoint's position in local space and a null velocity. That's all there is to the simulation. That position dictates where this virtual capsule points to, and this velocity, how fast it moves. And I say virtual capsule because it only mathematically exists here, in that blueprint. It's not an actual capsule component you can trace against or anything alike, right? Finally, if there are any simulated instances, well, time to simulate them, I guess. Now, in UE, UObjects are not ticked, so there's no tick event to use. So I could either use actors instead or use timers, but then timers come with certain constraints that was a bit annoying to deal with for this particular system. I won't bother you with the details. So my solution was to use this actor component stick, loop through all managers, and call that function and forward delta time. As simple as that. So time to dive into this function then. First, I accumulate the delta time. Here I get the list of participants. Then, to make this custom physics system be frame rate independent, I use substepping. So I divide that accumulated delta time to know how many subticks to perform that frame and consume it accordingly. Then I loop through all instances currently simulated in reverse order, so I can safely remove one entry during this loop. Next I get that instance transform, compute its capsule segment, same as I did before, loop through the list of participants, get that participant's position and see if it's near any instances. This is just a cheap squared distance check to very quickly see if it's worth doing the way more expensive capsule to capsule check. It's important to discard as many instances as early as possible. Anyway, if close enough to that participant, well, it still doesn't mean this instance is actually colliding with this participant's capsule, just that it's worth checking. So next, compute this participant's capsule segment and see if both capsules collide, and if so, push that instance away out of penetration. Now the way this works is the following. Let's assume this is our character, and this its capsule, from head to toe. And this is the Foliage instance and its capsule, from its instance position, its root, to its tip. And that tip is a position stored in the simulation stack, right? So at first, when initiated, it's the instance up vector multiplied by an arbitrary height multiplied by this instance scale in z. So this is in local space, relative to this instance origin. So if colliding, I increment that point's velocity by the character's velocity. But that instance also needs to be pushed away if the character is standing still, right? So I also add the penetration delta to that velocity. That's how much the character's capsule overlaps with this instance capsule. And that's pretty much it for the velocity for this participant. Repeat that for all participants to end up with a final velocity for that instance. Velocity applied here. The sum of that velocity and that instance previous velocity is used to push that point in a certain direction by a certain amount. I then get the direction from this point to that one, multiplied by the capsule's height to reproject that point onto a sphere. And because the simulation is in local space, the direction from that point, 0, 0, 0 to there, is really just that local position normalized. And that's a spherical constraint. And that's essentially how this mathematical capsule is made to pivot around the instance pivot point. Because this capsule is always oriented towards that spherically constrained simulated point. Next, I compute the velocity from the actual resulting delta movement and delta time. So I no longer care about the velocity I computed here, just the velocity described by how much that point moves this update once spherically constrained. And that's really important to get that angular momentum. It's a cheap hack, but it works quite well. Next, to have that point go back to its resting position, well, again I used a super cheap hack. Every single tick before that point is spherically constrained, I offset it along the instance up vector. That simple trick, with a spherical constraint constantly applied, makes the following behavior emerge. Finally, I decrease the velocity a bit every tick, that's drag, and voila, I get this effect. Neat. However, it looks a bit too rigid to mimic foliage in my opinion. Ideally, this instance would be mathematically made of multiple segments, and each would be individually simulated to create some kind of hierarchical bone chain, but that's not doable in blueprints, way too costly. So here again I cheat, and oh boy I cheat. Using a simple quaternion spring interpolation, it's like I create a virtual axis that tries its best to follow that capsule's axis. And that's the simulation in a nutshell. Not too complex overall, but again it results in quite a few nodes, and that starts to get costly to evaluate real fast with many loops. Now one question remains, how is that applied to the actual mesh? Well, actually, before even doing that, I check if I need to do that at all. Because that simulation update may actually have set that instance back to its resting state. So check that. Does that instance have any velocity left, or is it somewhat distant to its resting position? If not, this instance is removed from the simulation. Cool. But if still simulated, I get the simulation axis and send it to the static mesh instance using per instance custom data. But what the heck is that, you might ask? Well, let's start simple and let's add an instance static mesh component to an actor. Here's an option to tell how many custom data each instance is going to have. And that custom data is really just an array of floats. If each instance has one single custom data, then the first instance uses that first float, the second instance the second float, and so on. Two custom data, then that first instance uses the two first floats, the second instance the next two floats, and so on. So the memory cost of this feature is pretty simple to calculate. 32 bits per float, so that's 32 bits times the amount of instances times the amount of custom data per instance. Okay? And that array is then forwarded to the GPU, that way each instance has access to its own custom data in shaders. And thus you can very easily build per instance logic, say colorize each instance. So let's have, say, 3 custom data per instance to create an RGB value like so. Next, use that per instance custom data in shaders to build a color, either by combining those 3 custom data individually, or using that node that does the same exact thing. And that's pretty much it. So using this principle, I send per instance simulation data to each instance individually, and I build some kind of world position offset logic to have them bend and whatnot, right? However, there's one issue. When you have access to an instance static mesh component, you can tweak those custom data settings here. But what about Foliage? That's nowhere to be found. Well, by default, Foliage uses this default component class. So let's make a new one that inherits from that same class, like so. Set it here, and in that blueprint you can tweak those custom data settings. Neat. So here I used 6 custom data per instance. Why 6? Well, 2 pairs of 3 floats to create 2 XYZ axes. The first one is the direction this capsule points to, and the second one is that quaternion spring axis. That way I can bend that instance based on that first axis, at first, near the root, and then gradually switch to that other axis along the length, and that creates a curvature, and from that emerges this springy, bendy behavior. Now last bit of the puzzle, how those two axes are actually used to deform the mesh. Well, I feel like it's always the same kind of world position of the tricks I explain over and over in my videos, so I'll be brief here. I rotate vertices in local space using a simple transform matrix based on that instance forward vector and the simulations of vector. And actually, I use a vertical gradient derived from UVs to lerp those two simulation up vectors. Again, one is the capsule's axis, the second the quaternion spring axis. Some cross products later and I can come up with an XYZ coordinate system based on that lerped up vector to transform vertices and bend the mesh locally. Then I convert those vertices back to world space and convert that world space vertex position into an offset. And voila, here's how I made this per instance custom simulation. And that's in principle not so different from those fancy GPU-driven foliage simulations you can find in some games, like Alan Wake 2. Just that instead of computing all this on the CPU, either in blueprints or in C++, it's done on the GPU, and there's some kind of hierarchy going on to attach segments and create virtual skeletons and a GPU-based skinning method, and that's it. Now that's easier said than done. Most games today still rely on simpler systems using render targets and similar old-school techniques. That being said, the one benefit of using a simple CPU-based system like this one is that it's then super straightforward to have that system affect your gameplay. Like say, check how many instances are around a given participant at any given time. Use that count to drive, say, the walk speed so it's harder to move through tall grass. And maybe use some kind of threshold to say, hey, there are enough instances around, let's consider this actor hidden in tall grass and enable a stealth mechanism of some kind. That's at least what I try to showcase with this simple example. I simply fade in and out a simple post-process material when in stealth mode and voila. But I'll let you take a peek at the project in case you want to know more. Files are available at tier 2 reward on my Patreon. Voila, that's the end of the video. Thanks so much for watching and thanks for your support. Please consider leaving a like and subscribing to the channel if you like the video. Also, thanks so much to all my Patreon supporters, you're all much appreciated. Alright, I'll see you in the next video. Merry Christmas to you all, take care of yourself, bye bye!